All right, we are going to be doing notes 5.4. This is going to end up going over the fundamental theorem of calculus part 2, but not quite yet. We are going to talk about something called the cumulative area function first. So the cumulative area function is labeled a of x. That's pretty standard. And it's used to find the cumulative area between the function of the x-axis over some general interval where a is defined, that is your lower bound that you know, that's automatically chosen, and then whatever general x you feel like plugging in. So it's basically the area from a to whatever x value that you choose at any given time. And I'm going to write what the cumulative area function is first, and then I'll read my next paragraph. So it's a of x equals the integral from a to x. And then I'm not going to use f of x, I'm going to use f of t. Even if your function is called f of x, you're going to use something called a dummy variable. I'm going to read my paragraph and then I will show you why. It says, note that the variable of integration is different than the upper bound variable. This is intentionally done to avoid confusion. If the function you wanted the cumulative area for has x as the independent variable, like if this graph said f of x over here, then you would just replace that with any other variable when integrating. So you could use t, that's pretty standard. Variable, the dummy variable, or the replacement variable. And I'm going to show you why. So let's say that I had an x here. I just left that as f of x instead of f of t. Then I get my antiderivative. And what's the antiderivative of f of x? Capital F of x. Now you might see that and think, oh, you're done. Maybe not. Maybe you remember that you actually need to plug in the bounds. Well, this looks weird because you already have an x to go in the first place. Feel okay to you, but it's not good practice. We want the variable that we have in our integrand to be different than the variable that we are plugging into it, just because it's best practice. So do me a favor, get over it if your head is just not wanting to quite accept that loose reasoning for it, and just do the dummy variable. It's just what best practice calls for. So I'm just going to use a t. Area function of f of x equals 3x to the negative 1 minus 7 with a lower limit of a equals negative 1. Now, if I asked for a cumulative area function, that integral is perfectly fine. Technically, it's an area function, but I asked for a formula. So what I would like you to do is actually do that integration. That way you have a nice formula that you could easily calculate without having to do an integral every single time. So let's go ahead and write our area function. It should be a of x. What are your bounds going to be? X. And then in our integrand, we want to use our dummy variable. Remember that. So because I have f of x here, I'm going to replace that with a dummy variable of t. You can use whatever letter you'd prefer. All right, go ahead and get your antiderivative. The antiderivative of 3t to the negative 1 is 3 ln absolute value of t. And then minus 17. Plug x into it. So go ahead and evaluate your antiderivative. You're going to do upper bound minus lower bound. Remember that. All right, so we get 3 ln absolute value of x minus value of -1 is really 3 ln of 1. And the natural log of 1 is 0. So this actually goes away because it's 0. And then -7 times -1 is +7, but this negative from over here makes that a -7 again. Now, one thing we have to be careful of is when we notice that we have functions with domain restrictions, remember what the domain restrictions are going to be. So looking at my original function, and you could even just look at your antiderivative as well. My original function is really 3 over x minus 7. That function is not defined at 0. So when I go to integrate it, I'm either going to have to integrate on numbers less than 0 or numbers greater than 0. I can't integrate over that discontinuity. So that means that x is going to have to be less than 0. That way I'm staying on the left side where that -1 is. And if you want to write the domain discontinuities in your original. So this right here would be the cumulative area function formula for any cumulative area from -1 to whatever x value you choose to plug in that interval. What I would like you to do right now is go ahead and calculate the derivative of that area formula that you just came up with. Is 0. Hey, isn't that what we had for f of x in the first place? That is not a coincidence. So that brings us to the fundamental theorem of calculus part 2, something that I kind of hinted at in, I think, homework a few lessons ago. So the fundamental theorem of calculus part 2 says that assume a function is continuous on an open interval I, continuous, that's our first criteria. Then its associated area function, a of x, is an antiderivative of f of x. Right, because it's the result of your integral. That is to say the other way around, that if I were to take the derivative of my antiderivative, I would get f of x. So basically, if I have my integral, and you might want to just see me write this first. If I have my area function, a of x, I'm just going to write the general one. And I go to do the derivative of that. So I'm going to use my derivative operator. Do you notice how it's kind of like the integral and the derivative operator cancel each other out, and then that upper bound variable gets replaced into my integrand? So I'm just left with f of x. Or I could put that over here. I think I might actually do that. So that is what the fundamental theorem of calculus part 2 deals with. It's basically taking the derivative of an integral and realizing that you're just left with that integrand with whatever variables in that upper bound. Now this works when it's just a variable up there. If you do not have a variable up there, you're basically just taking the derivative of area, which is a number. And what's the derivative of a number? 0. All right, so let's go ahead and do example 2. It says let a of x equal that area function. Go ahead and calculate a prime of 2. Remember, whenever we are calculating the derivative, we want to do the general derivative first. So figure out what a prime of x is for me first and foremost. You don't need to write this next part, but I'm going to. You could just write the final result if you know that right off the top of your head. Okay, so you could technically go ahead and evaluate your area function integrand and get a nice formula like we did back in example 1. And then you could end up taking the derivative like we did in part B. But do you notice how you'd have to multiply 5t minus 9 out 4 times before you could even get to doing the integration? That's not fun. That's why we just learned about FTC part 2, where if we take the derivative of the integral, it's like they cancel out, and then that variable is passed into your integrand. So I would actually be left with 5x minus 9 to the 4th power as my a prime of x. And now you can calculate what a prime of 2 is. So that's 10 minus 9, which is 1. 1 to the 4th power is 1. One thing that I do also want to address here is, why does the lower bound not matter? If it was also another variable, it would actually. And we want to kind of separate these up into 2 different intervals where we're getting numbers as our lower bounds. But it's because when you go to do your area formula like we did in 1A, that lower bound, those are going to be all just regular numbers. And when we go to take the derivative of those regular numbers, you get 0. So they disappear. They have no sort of role in the derivative of that integral or of that antiderivative. So that's why the lower bound, when it's a number, doesn't really matter. All right, let's go to example 3. Let a of x equal the integral from 4 to x of f of t dt, where f of x is graphed below. So it's the cumulative area from 4 to whatever x value you want to go to. It says, where does a of x have local max and local min? So really quick, how do we find local extrema? Remember, first and foremost, it's where a of prime of x equals 0 or does not exist. And then for our max, it's going to be where a prime goes from, let's see, positive to negative. And then the min is where a prime goes from negative to positive. So let's go ahead and figure out what a prime is. Actually, I'm not going to bother writing that again down here. I already have a of x written up top. So just imagine doing your d dx on that. What happens? The derivative cancels with your integral and we can pass x inside. So a prime is f of x. So figure out where that equals 0. And remember, local extrema cannot occur at endpoints. So we're not looking at negative, or we're not looking at 0 or 6. So it looks like our function equals 0 at 1.5 and at 4.5. So let's go ahead and make our first derivative number line, which is actually just our f number line. And go ahead and write down your F values around those points. So before 1.5, which is here, we have negative values. And then after 1.5, we have positive values. And then after 4.5, these are all negative values. So it looks like A of X has, oops, a local min at X equals 1.5 and a local max at X equals 4.5. Now let's figure out what those actual values are. So I want to figure out what A of 1.5 is and what A of 4.5 is. I'll do 1.5 first. And remember, the definition of A of X is that integral from, let me see, I believe it was 4 to X. So instead of X, I'm going to put 1.5 there. And then before I go into this, keep in mind that the integral represents what? The area under the or between the function and the x-axis. And when I'm calculating the area using geometry and not just like algebraically, I need to pay attention to the bounds. My bounds are out of order, so I am going to go ahead and switch them by making the integral negative. So go ahead and calculate that. I'm going to put my work up. In 3, 2, 1. So I'm getting negative 2.25. And then figuring out what A of 4 is, or I'm sorry, A of 4.5. Still 4 is that lower bound. I'm just replacing that X upper bound with 4.5. And keep in mind here that these bounds are in order, so I do not need to do any sign switches. So if I go from 4 to 4.5, that is just the area of this little triangle right there. So that's just 1/2 times that base of 1/2 times the height of 1, and I'm getting a height of 0.25. Okay, so let's move on to example 4. Determine the area function by evaluating the integral. Okay. Ooh, so notice this time we don't just have a plain x in that upper bound, we have an x cubed. This is going to lead into what you see at the bottom of the page. So we're just investigating here, and then we're going to draw a little conclusion for later. And this, I think, is even more important that you have a dummy variable, because you would see an x and then you're like, oh no, I need to plug in an x cubed. So having that dummy variable, especially when the variables are a little different or they're different variations of each other, I think it's key. So antiderivative is what? See, t squared, and then I'm going to take the 2 coefficient divided by 2, that's 1. Not going to bother writing that. And then minus 5t. All right, plugging in my upper bound. So that's going to be x cubed squared minus 5x cubed minus, and then, you know, this time I really do prefer switching the signs on when I plug in the lower bound into my antiderivative. That's just skipping a step. It's basically you just distributing the minus to the antiderivative of your lower bound. So I'm just going to do that right off the bat. So that would be minus t squared with negative 4 plugged in. plus 5t with a -4 plugged in. If you don't like that, go ahead, do your sets of parentheses, that's fine. All right, so we get x to the 6th power minus 5x cubed. See, -4 squared is positive 16, but I have that negative there, so it's negative 16. And then that's minus 20. Negative 16 minus 20 is going to be negative 36. So what I would like to notice here is what happens when we factor out, or when we take the derivative. Go ahead and take the derivative of that area function, see what you get. And then the derivative of negative 36 is 0. What I would like you to do is also factor out the GCF here. What do you notice is your GCF? Definitely have an x squared and I have a 3. I want you to compare this and this to things that you might notice from part A. Or not even part A, but the instructions in part A. Is there anything in the area function, how it's defined, that you can relate to these two parts? So here's personally what I'm noticing. This, that looks like the integrand, but with the upper bound plugged in. I think that's hopefully at least something that everybody should have noticed. And then where do we think that we might be getting that from? If you were to compare anything from your original function. Hopefully you notice that that looks like the derivative of your upper bound, which is x cubed. So that leads us into fundamental theorem of calculus part 2 of chain rule, but it's not like a normal chain rule. It's chain rule where that upper bound is something other than a plane X. So kind of in that sense. So it kind of goes here. If I have an area function, let's just call it g of x, or we can call it a of g of x. If I go to take the derivative of that, all right, you know what? Let me write this down here. Hold on. So that would be a g of x this time. Okay. So if I were to take the derivative of that, I have to be careful with this notation right here, because technically if I put the prime here, we're kind of looking at chain rule. So I'm going to do d dx here. I put t, I don't know why. Think about what happens with chain rule. Technically, I would take the derivative of the outside. So I'd take the derivative of my area function with g of x inside. And then I would multiply by the derivative of the inside. So here what happens is when I go to do my d dx here, remember it's like the derivative cancels out with your integral and you essentially plug that into your function. So it'd be like f of g of x, which I think I might just type. Times the derivative of g of x. Which is basically what we had in that last problem. So for our very last example, we have something other than a plain x in that upper bound, and we have that constant in the denominator, so we don't, or in the lower bound, so we don't need to bother with it. I want you to figure out what g prime of x is. Okay, so remember, derivative kind of cancels with your integral, and you plug that upper bound in. So we get cosine cubed of 1 over x times the derivative of 1 over x. What is the derivative of 1 over x? So let me just check and see, is that going to be ln of x, or do I need to do power rule? So if I multiply by that power, -1x to the -2, yeah, that's power rule. Otherwise, I would have had the x disappear. So this is our derivative of that function. If you have questions, definitely make sure that you ask.